Let's talk about power. No, not that kind of power. Electric power. It takes energy to light a light bulb, and it takes energy to move hundreds of pounds. In both cases, though, the rate at which that energy is used is called power.
Let's go back to our weightlifter. It turns out that moving heavy objects makes for a great example of explaining power. Moving 100 kilograms through the air requires you to spend a good deal of energy. However, moving the same 100 kilograms across the same distance more quickly requires the same amount of energy, but you need more power. In the 1780s, the Scottish inventor James Watt greatly improved the design of the steam engine, which helped bring about massive advancements in the Industrial Revolution. He also coined the term horsepower to compare the output of steam engines with the power of draft horses. Thanks to all that, the SI unit for power is now the watt. I mentioned that power is a rate, much like speed is a rate. For example, miles per hour or kilometers per hour tells you how far you've traveled for a given amount of time. A watt is equal to 1 joule per second, and it shows how much energy is spent or transferred with respect to time. For example, if it takes 3 seconds to expend 900 joules of energy to move a weight over your head, you'll need 300 watts of power. Now, if you spent the same amount of energy lifting the same weight, but did it in only 1 second, you'd need 900 watts of power. You can actually try this yourself. Try taking a heavy object, like this dumbbell here, and moving it about 1 meter in the air, but make it take about 3 seconds. Now, try moving that same object the same distance, but do it in 1 second. You'll notice that it takes a lot more effort on your part. Athletes often refer to this as explosiveness, doing a movement or moving a heavy object very quickly. With that understanding of power, let's see how this relates to electric power. I've already mentioned that 1 watt is equal to 1 joule per second. We know that the volt is equal to 1 joule per coulomb, and the ampere is 1 coulomb moving past a point per second. If we were to multiply a volt times an ampere, we could cancel out the coulomb units and we'd get 1 joule per second. Hey, that's the definition of a watt. So, we can safely calculate electric power as voltage times current. Let's try this with an example.
Once again, I've hooked up a resistor to my trusty power supply and cranked up the voltage to about 3.03 volts. We can see that about 0.03 amps are flowing through the circuit, and with that information, we can calculate electric power.
Using our equation from earlier, P equals V times I, we can plug in 3.03 volts and 0.03 amps. With some multiplication, we can see that the resistor is consuming 0.0909 watts. What do we mean by consuming power? Well, since energy can neither be created nor destroyed, it's not really fair to say that something is consuming power like you're eating it. However, when we're talking about power consumption in terms of electrical components, we really mean the ability of that component to convert electrical energy into some other form of energy. In the case of our resistor, electrical energy is being converted to heat. All atoms vibrate randomly, and that vibration corresponds to the temperature of the material. The more the atoms are vibrating, the hotter the object is. Now, as electrons move through a material like copper wire, they will ultimately bump into some of the atoms, which causes the atoms to vibrate even more. This results in the material heating up. Resistors are made specifically to cause more of these collisions, and therefore restrict the flow of current, but it also means that they get hotter the more current they impede. This is a rather large 8 ohm resistor, and this is an infrared thermometer that lets me read the surface temperature of objects at a distance. Right now, there's no electricity flowing through the resistor, and it's reading about 24.5 degrees Celsius. If I apply 8 volts across the leads, about 1 amp will flow through it, resulting in about 8 watts being converted to heat. Now, if we measure it again, we see that the surface temperature has risen by about 4 degrees. That's the magic of energy conversion.
We can use all that heat for something useful. What I've got here is an incandescent light bulb, and in it is a very special resistive element known as a filament. When the filament gets hot enough, it begins to emit visible light. So, when I give it some electric current, I get light. After a while, though, the bulb gets hot to the touch as a result of restricting all that current. And, as it turns out, incandescent bulbs are very inefficient, as most of the electrical energy is converted to heat, not light.
We can use the heat from resistors for other purposes, however. Most toasters rely on resistive elements to turn bread into crispy toast. Some space heaters use a similar element to keep your legs warm on a cold winter day, and older electric stoves also rely on resistance to convert electricity to heat in order to cook your dinner. So remember, your electrical devices aren't consuming power in the sense that they're eating it, but they're converting electrical energy into something else, like heat, motion, or sound. Speaking of eating, I need to convert some electrical energy to heat to make myself some lunch.